Greetings to everyone here with us today. As we jump into chapter 7, I hope you will all be pleased with our discussion. By the way, I'm Hershey Yabut, along with my group mates. Our presence is with you to expound and relate the problem about the 7 bridges of Konigsberg to networking, also to define and construct the different types of graphs, to differentiate between paths and circuits, the Euler and Hamilton theorems, and to apply these theorems and algorithms as solution to problems. Without further ado, the story of graph theory begins at Königsberg, Russia, now named as Kaliningrad, Russia. The city was built around 2 islands in the Pregel River, connected by 7 bridges. The citizens in the city built their bridges to cross around and for trading purposes. As they wander every Sunday afternoon, they all come up with a game in which the goal is to travel around the city using bridges exactly once. Leonhard Euler is an 18th century Swiss mathematician and considered as the founder of graph theory that made a significant contribution in advancement of mathematics. He also developed the first theorem of graph theory in 1736 to provide a solution to a prevalent puzzle of Königsberg bridge problem. Clearly, bridges of Königsberg has historical significance in mathematics, because Leonhard Euler laid a foundation for another branch of mathematics known as graph theory. In layman's terms, a graph theory is a branch of mathematics with the networks of points connected by lines. Now, with the graph theory, we are able to illustrate this network of bridges as vertices and lines connecting those vertices in order for us to predict if it's traversable or not. So, if we can cross over each bridges exactly once, that means the bridges of Königsberg is traversable. We will going to find out on our next slide. But before we bump into our lesson, let's have these simple graph first. For the first graph, is it possible to trace this shape without going the same line more than once? Now let's have a look for the solution. Hooray! Let's go to the second graph. Is it possible to take each side without lifting your pens? Now, let's have a look for the solution. Now that we successfully analyzed the graphs, we can now conclude that the first graph is traversable, while the second graph is not traversable. So, what's Euler's circuit? Simply, it is in Euler's theorem. A circuit that uses every edge in a graph with no repeats. A network is consist with vertices or vertex and lines. Vertices or vertex such as point A, point B, point C, etc. And lines such as line AB, line BC, line CD, and so on and so forth. Then there's called an even degree vertex that has even numbers of sides connected to it. The even numbers are 2, 4, 6, 8. And odd degree vertex that has odd numbers of sides connected to it. Odd numbers are 1, 3, 5, 7, 9. For us to completely predict the outcome of the graph, whether it's traversable, Euler also provides 2 conditions. First is that all of the vertices are even degree, and the second one is exact 2 vertices are of odd order and the rest are even. As presented, here's a topological map of Königsberg along with its topological graph. To explain it in detail, let's consider this land area as vertices or points. From point A, we can go to point C by crossing bridge number 1 or bridge number 2. From point A, we can go to point B by taking bridge number 5 or bridge number 6. Once again, from point A, we can go to point D by crossing bridge number 3. Coming from point C, we can take bridge number 4 heading to point D. Also from point B, we can take bridge number 7 heading to point D. Alright, we can now apply these two conditions of the network to know if this bridge of Königsberg is traversable. So, from vertex C, it has 1, 2, 3 odd order vertices. From vertex A, it has 1, 2, 3, 4, 5 odd order vertices. From vertex B, it has 1, 2, 3 odd order vertices. And from vertex D, it has 1, 2, 3 odd order vertices. Since all of these vertices are in odd order vertices, we already failed to satisfy the two conditions of traversable graph. We can now conclude that the bridge of Kaliningrad, Russia is not traversable. It is clearly far from reality to see possibility for us to visit each city and cross over all of 7 bridges at exactly once.
After knowing the history or the background of the topic, we will now define what a graph theory is. So ano nga ba ang graph theory? In discrete mathematics, it is a simply study of the graph. A graph is determined as a mathematical structure that represents a particular function by connecting a set of points. It is used to create a pairwise relationship between objects. Another definition for the graph, it is a set of all points called the vertices and line segments or curves called edges that connect vertices. It is also a subfield that deals with the study of graphs. It is a pictorial representation that represents the mathematical truth. Katulad ng sinabi ko kanina, graph is a pictorial representation. So we have 3 examples here that we can use graph in many different scenarios. So unang example natin is a representation of baseball team. So in this picture, each vertex represents a baseball team. And yung edge connecting vertices may mean 2 teams competing against each other. Pangalawang example natin is it shows computer network of a small businesses, where each vertex, yung mga dulo niya uli, is nagre-represent ng computer and yung mga edge are machines na directly connected to each other. So pangatlo is yung graph can also be used to represent the flights available on a particular airline between a selection of cities. So, uli, yung vertex niya is nagre-represent ng city and yung mga edge niya na nagko-connect sa 2 cities means that there is a direct flight between the 2 cities. So I want you guys to take note na the placement of vertices has nothing to do with geographical location. Yung vertices can be shown in any arrangement na pipiliin natin when we are making a graph. The most important information is which vertices is connected by edges. Sa pagko-construct ng graph, we must know the basic properties of it. So, meron tayong dalawang basic property na itatackle wherein makikita mo siya sa paggawa o sa paghahanap mo ng kahit anong type of graph. So, the first one is yung vertices or yung nodes. Ito yung mga points where the edges meet in a graph. So, pwede siya mag-represent as a physical object or yung mismong concept mo and yung abstract entity depende sa choice mo. Pangalawa is yung edges. These are the connections between vertices. Or ito yung mga lines na nagko-connect between 2 points. Edges can be directed, means isa lang yung papatunguhan niya, and undirected or bidirectional, meaning pwede siyang pumunta sa dalawang direction or opposite from each other. There are different types of graph. The first one is directed graph. It is also known as diagraph. This is a graph made up of a set of vertices connected by edges, in which yung mga edges niya is direction associated with them. We can say na directed yung edge niya by the help of arrows. Pangalawa is undirected graph. Dito naman sa graph na to is where the set of nodes are connected together. And all the edges here are bidirectional. Meaning, lahat sila is walang iisang direction. This type of graph is also known as undirected network. Third is null graph. Ito yung pinakamadaling gawin na type of graph because it has no edges between vertices. So basically, puro lang siya vertices or points. And it is also called as empty graph. Next is complete graph. Bakit nga ba to tinawag na complete graph? Because it contains all possible edges. Sa graph na to, in every pair of vertices, it is joined exactly by one edge. Meron din tayong tinatawag na connected graph, in which pwede magkita o mag-visit from one vertex to any other vertex. Mapa one edge man, multiple edges, or pwede ring with a loop.
Now that we know what a connected graph is, the next type of graph is a disconnected graph. A disconnected graph is a graph where not all the points or vertices are connected to each other. The examples shown are disconnected graphs. A disconnected graphs also consist of more than one components, and each component is called a subgraph. As mentioned before, a graph can contain a loop. So what is a loop? A loop is an edge that connects a vertex to itself. That means that you can only go from point A to point A and not go to any other point. Then what about a multiple edge? A multiple edge is an edge where two or more edges connect to the same vertices. Now we will be constructing a graph using this table. In this table, it lists 5 students at a college, and X indicates that 2 students participate in the same study this semester. Using the table, we can now create a graph. So to make a graph, each vertex will have to represent a student, and each ed will represent a common study group that the 2 students participate in. So we will also answer 3 questions. For the first one, which student is involved with the most study groups? The second one, which student only has one study group? And lastly, how many study groups does Laura have? Using the information that we have from the table and following the instructions, we will end up with this graph. So using the graph, we can now answer the questions in letter B. In the first one, we want to know which student has the most number of study groups in common with the others, which is obviously Amber, because Amber has 3 study groups in common. And for the second one, Kayla is the only student that has 1 study group in common with the others. And for the final questions, Laura's vertex is connected to Amber and Matt, so she has 2 study groups. Next, we will tackle equivalent graphs. Equivalent graphs are graphs wherein edges form the same connection of vertices, regardless of how we arrange them. So in the example, each graph looks different to each other, but all graphs have the same connection to vertex B. So in each graph, we have the same edges, that is AB, BC, BD, and BE, and no other edges exist. In this example, all the edges are still the same and the other edges do not exist. So this is an equivalent graph. Though the 2 graphs may look different, all the connections are still the same. So graph 1 and graph 2 are equivalent. For the next one, graph 1 and graph 2 are not equivalent graphs. And why is that? It's because even though the 2 graphs look the same, and the vertices are in the same location, the connections are not the same. The edges are also not the same.
Good day everyone, I am Nicole and I'm going to discuss Euler paths and Euler circuits. So before we proceed with our topic, let us first define what is a path and what is a circuit. A path in a graph is like a journey or a route that you can take from one point to another by following a series of connected lines or edges. On the other hand, ang circuit or closed path, ito naman yung klase ng path na nag-i-start at nagtatapos sa same vertex. For example, in this figure, path ADFG EBA is a circuit kasi nag-start siya sa A and nag-end siya sa same vertex na A. While path ABFGEH is not a circuit kasi hindi siya nag-begin and end at the same vertex. Ngayong alam niyo na ang ating mga key terms, proceed na tayo sa ating topic. Euler path. Ito yung klase ng path na ginagamit ang lahat ng edges sa graph exactly at once, as in isang beses lang. So may tinatawag na Euler path theorem. Ito yung mathematical statement that provides conditions for the existence of Eulerian paths. Sinasabi dito na sa connected graph, magkakaroon lang ng Euler path if and only if ang degree ng vertices ay odd number. Wait, ano muna yung degree? It refers to the number of edges connected to the vertex. Basically, kung ilang lines or edges ang nakakonect sa vertex, yun ang degree. Isa pa dito, ang Euler path daw ay dapat na mag-start at mag-end sa vertex na may odd degree. Proceed naman tayo sa Euler circuits. It's like an Euler path, pero ang pinagkaiba lang nilang dalawa is ang Euler circuit ay nag-i-start at nagtatapos sa same vertex. Siyempre, kung sa Euler path may theorem, siyempre sa Euler circuits din, at ang tawag dito ay Eulerian graph theorem. Ito naman yung mathematical statement that provides conditions for the existence of Eulerian circuits. Sinasabi dito na sa connected graph, magkakaroon lang ng Euler circuit if and only if ang degree ng lahat ng vertices ay even number. So for example, the path BD, FG, HE, CBA, DGEB in the figure is a Euler circuit. Why? Kasi nag-start tayo sa vertex B and also nag-end tayo sa vertex B. Isa pa, ginamit natin ang mga edges exactly at once. Kaya naman na-follow natin ang condition ng Eulerian graph theorem. So recap lang, masasabi nating may Euler path kapag ang degree ng dalawang vertex ay odd number. Kapag Euler circuit naman, ang degree ng lahat ng vertex ay even number. Isa pa, dapat na isang beses lang magagamit ang mga edges. Take note of the word traversable. Traversable means you can move through or you can travel through a path without getting stuck or blocked. Essentially, sa network, para masabi mo siyang traversable, kailangan na kapag nag-draw ka ng continuous stroke sa path, ay hindi mo malilift ang pen or pencil from the paper and hindi mo tinatrace ng dalawang beses ang edge. So, may mga senaryo paano mo malalaman if ang network ay traversable or not. Una, kapag walang odd vertices ang network, ito ay traversable. Dahil kahit sa ang vertex, pwedeng maging start at ending point. Kapag naman may isang odd vertex, ang network ay hindi traversable kasi a network cannot have only one starting or ending point without the other. Kapag may two odd vertices, ito ay traversable. Ang isang odd vertex ay magiging starting point at ang pangalawa ang magiging ending point. And lastly, if more than two na ang odd vertices, hindi na siya traversable dahil ang network can only have one starting and ending point. Basically, magiging traversable lang ang ating network if and only if wala or may dalawa tayong odd vertices. So let's have an example. Graph A and D is traversable kasi wala siyang odd vertices. Graph B, C, and E are also traversable since meron siyang dalawang odd vertices. Meanwhile, graph F is not traversable since meron siyang apat na odd vertices. And that's all for Euler paths and circuit. Let's hear naman ang mga applications nito.
Hello everyone, I'm Sam Manlisis. Now that we finished discussing about the Euler path theorem, let's see the examples and applications of it that may occur in the real world. For the first example, a photographer would like to travel across all the roads shown on the following map. The photographer will rent a car that need not be returned to the same city, so the trip can begin in any city. Is it possible for the photographer to design a trip that traverses all the roads exactly once? So to solve this, the first thing we must do is to see if the route is an Euler path. So applying the Euler path theorem, to know if the route is a Euler path, we must find the degree of each vertex. The graph must have two odd vertices and all the other vertices must be even for it to be considered as an Euler path. So pag binilang natin, 3 yung degree ng Alameda, 4 sa Burley, 2 sa Caldwell, 3 sa Dover, 2 sa Evanston, 4 sa Fairmount, at 2 sa Grangeville. All in all, 2 odd vertices and 5 even vertices. So based sa theorem, the route is an Euler path. So going back to the question, is it possible for the photographer to design a trip that traverses all the roads exactly once? The answer is yes. Just keep in mind na we should start the path sa ating odd vertices, which sa case na ito ay sa Alameda o sa Dover. So, ito ang sample route. Simula sa Alameda, papuntang Burley, Caldwell, Dover, pabalik sa Burley, then Fairmont, pabalik sa Alameda, then Grangeville, pabalik sa Fairmont, then Evanston, and lastly sa Dover. Now, let's go to the second example. The floor plan of an art gallery is pictured below. Draw a graph that represents the floor plan, where vertices correspond to rooms and edges correspond to doorways. Is it possible to take a stroll that passes through every doorway without going through the same doorway twice? If so, does it matter whether we return to the starting point? So, para di masyadong complex, isimplify muna natin yung mga room. Gawin natin siyang graph. So, let's make every room a vertex, and the doorway connecting the rooms will be the edges. After simplifying it to a graph, i-apply lang uli natin yung ginawa natin kanina, which is alamin kung ang graph ba ay Euler path. So, ang vertex A ay may 2 degrees, 4 sa B, 3 sa C, 3 sa D, 2 sa E, at 6 sa F. All in all, 2 odd vertices and 4 even vertices. So, the graph is an Euler path, and the starting point can be vertex C or D. So, let's go back to the question. Is it possible to take a stroll that passes through every doorway without going through the same doorway twice? The answer is yes, because the room is an Euler path. The follow-up question is, if so, does it matter whether we return to the starting point? The graph or the room is an Euler path, and it is not an Euler circuit, so it is not possible to go back to the starting point while passing through every doorway only once. In simpler terms, kung sa vertex C tayo nagsimula, dapat sa vertex D ang ending and vice versa. That way, magiging Euler path pa rin ang graph natin. Yan, tapos na tayo sa ating examples. Other applications pa ng Euler path or circuit ay ang supermarket problem, police patrol problem, floor plan problem, at water pipe problem. Hindi ko na iisa-isahin ang mga yan dahil halos parehas lang sila sa ginawa natin at i-discuss din ng kagrupo ko ang floor plan problem. Yun lang para sa applications and examples ng Euler path theorem. Thank you!
Hi, I'm Michelle James Sangkay and I'm going to share to you about the floor plan problem. But first, let's understand the key term, traversability. Traversability means moving through a space like a floor plan problem, for an example, to visit all rooms and doors without needing to return to the starting point, offering flexibility in the path taken. The floor plan problem is related to the Königsberg Bridge problem. Why? Because both involve traversing a network while adhering to specific rules. The rules in here is that you must traverse all rooms and pass through each door but only once. Here, it doesn't require an Euler circuit. Why? Because like I said, it focuses on achieving traversability rather than specific path that visits each room and door exactly once, as the Königsberg Bridge problem does. Here, it focuses on achieving traversability rather than ending the trip where it began in Königsberg problem. Let's take a look on this figure for an example. Let's label the room as A, B, C, D, E, and F. Note that in figure A, rooms A, C, E, and F have 2 doors, and rooms B and D have 3 doors, while in the figure B, there are only 5 doors. But there's a door leading outside, so it is still counted as a room. Thus, figure B has 6 rooms labeled as A, B, C, D, E, and F. Rooms A, B, and C each have 5 doors. Rooms D and E have 4 doors. And room F has 9 doors. Solution for this is to classify each room as even or odd according to the number of doors in the room. Note that a solution is only possible if there are no rooms with odd numbers of doors or if there are exactly 2 rooms with an odd number of doors. In figure A, there are 6 rooms and rooms B and D are odd, so we can say that this floor plan can be traversed. The solution here requires that we begin in either rooms B or D and then finish in the other. While in figure B, there are 6 rooms and rooms A, B, C, and F are odd with D and F as even. Since there are more than odd rooms, this floor cannot be traversed. But if one of the doors connecting 2 of the odd rooms is blocked, then we can say that this floor plan can be traversed. In the end, let us try to identify what Euler actually did. So Euler's proof regarding the existence of an Euler circuit in a graph was actually based on several observations. The first of this is the vertex degree. Euler examined the number of edges that met at each vertex in the graph. He then noticed that to complete the desired path, or the Euler circuit, every time you approach a vertex, you would have to leave that vertex. Next is the even degree requirement. For an Euler circuit to exist in a graph, it was necessary that the degree or the number of edges connected to of every vertex had to be an even number. Because for every entry into a vertex, there had to be an equal exit, which could only happen with an even degree. And lastly, Eulerian graph. Euler's work led to the conclusion that graphs with even degrees at every vertex are called Eulerian graphs. These are the only types of graphs in which an Euler circuit can exist, allowing a closed path that covers every edge exactly once. That's all. Thank you.
Hi! Does your parcel from online shops arrive on time? If not, maybe the rider is looking for where you at. Great! This concept would definitely helpful for you. What is Hamiltonian circuit? In 1857, Sir William Rowan Hamilton invented a puzzle game called the Icosian game, a closed loop that visited every hole exactly once. By definition, a Hamiltonian circuit is a path in a graph that uses each vertex exactly once and returns to the starting vertex. Which means a Hamiltonian circuit starts and ends at the same vertex. However, a Hamiltonian path also visits every vertex once without repeating but does not have to start and end at the same vertex. Meaning a Hamiltonian path starts and ends at a different vertex. Unlike the Euler circuit, there is no theorem that allows us to instantly determine whether or not a Hamiltonian circuit exists for all graphs. To see if we all catch up, let's find the Hamiltonian path and circuit in each graph. Dirac's theorem is proposed by Gabriel Andrew Dirac, a Hungarian mathematician in 1952. He states that in a connected graph with at least 3 vertices and no multiple edges, if n is the number of the vertices in the graph and every vertex has degree of at least n over 2, then graph must be Hamiltonian. We use the Dirac's theorem for us to be able to determine if the graph is Hamiltonian. Now let's take this graph as an example. Available flights of a small airline. An edge between 2 vertices in the graph means that the airline has direct flights between the 2 corresponding cities. So, in this graph, we could say that Portland and Reno has direct flight. Now, we have to look for the number of vertices. So we have 6 vertices. And every vertex of the graph has a degree at least n over 2 equals 3. Like in Portland, it has a degree of 3. In Butte, it also has a degree of 3. In Boise, it has a degree of 4. We can say that the graph is Hamiltonian because we've met the condition of the Dirac's theorem. Since this graph is a Hamiltonian, we can find a Hamiltonian circuit. So a Hamiltonian graph contains a Hamiltonian circuit. And keep that in mind that the Dirac's theorem only determines if the particular graph is a Hamiltonian.
Now moving forward to our next topic, which is the weighted graphs. A weighted graph is a graph in which each edge is associated with a value called a weight. The value can represent any quantity we desire. So, itong weighted graphs na to, sinasabi na each edge or yung line na point to point, meron silang value or meron silang numbers na kaakibat. So, tinatawag itong mga numbers na to or value na to na weight. Makikita natin sa illustration na itong mga point-to-point natin, for example, QC to Manila, meron silang value na katumbas, which is 10 km. For example lang guys, yung 10 km or yung mga other kilometers distance na yan is gawa-gawa lang and hindi siya appropriate sa tama or tugma sa totoong buhay guys. So, itong mga weighted graphs na to is, pwede natin siyang i-associate or i-connect sa Hamilton circuit na didiscuss kanina. For each Hamiltonian circuit in the weighted graph, the sum of the weights along the edge gives the total distance traveled along the route. So, kapag sinabi natin na pupunta tayo sa QC to Manila, then Manila to Pasig, itong mga weight na to na 10 km and 5 km, which is yung point to point, is sinasabi na kapag pinag-add natin tong dalawang value na to or dalawang weight na to, is ibig sabihin yun yung total distance na nakuha or nagawa mo sa travel na ginawa mo. So now, para mas maintindihan natin kung paano ba ina-apply itong weighted graph sa Hamiltonian circuit or kung ano ba yung purpose na itong weighted graph sa buhay natin, meron tayong hinandang example problem para sa inyo. So before yan, ano nga ba ulit muna yung Hamiltonian circuit? Yung Hamiltonian circuit or Hamilton circuit is for example, meron tayong table or graph. Meron tayong graph. And dun sa graph na yon, meron tayong mga vertex, di ba? Merong vertex or meron tayong points. So, for example, nagsimula ka sa point 1. Tapos may 4 pang point. So, point 1, point 2, point 3, point 4, and point 5. Kailangan magsisimula ka sa point 1, then makapunta ka sa lahat ng points simula 2 hanggang 5 nang hindi ka bumabalik sa mga point na yon. And for example, pupunta ka na sa last point mo, which is yung point 5, kailangan makabalik ka rin sa point 1 kung saan ka nagsimula. So, for example, ganito, sa problem natin, suppose a traveler would like to start in Quezon City, visit the other 4 cities, and return to Quezon City. Find 3 different routes that the traveler could follow and find the total distance for each route. So, ang sabi dito na from makikita natin sa illustration, yung traveler nasa Quezon City siya. So, gusto niya pumunta sa iba't iba pang city, which is yung Manila, Pasig, Bulacan, and Pasay. So, kailangan sa Hamiltonian circuit na rule is pupunta siya from QC, pupunta siya ng Manila, pupunta siya ng Pasig, Bulacan, Pasay nang hindi nauulit. Pero kailangan makabalik din siya sa Quezon City. So, ang gagawin natin ay hanap tayo ng 3 ruta na mas madali para dito sa traveler na to. So, pwede rin nating gamitin yung table na to na makikita rin natin sa screen natin. Pwede natin ilatag lahat ng mga value na nakikita natin sa plane or sa graph na meron tayo. So, nilagay ko lang dyan yung mga places and yung mga katumbas na value nila from point to point. So, either way, pwede kayong tumingin sa kahit saan dyan para i-identify yung value na meron itong mga line or mga edges natin. So, sa unang ruta, which is makita natin yung red, bumuo tayo ng ruta sa QC, Manila, Pasig, Pasay, Bulacan, and pabalik ng QC. Kung makikita natin, hindi tayo bumabalik sa kahit anong points or kahit anong lugar. Bale, isang straight lang siya pabalik ng QC. So, itong QC to Manila, di ba meron tayong makikitang value sa gitna nila, which is yung 10 kilometer. Itong Manila to Pasig, nakikita natin na may 5. Pasig to Pasay, makikita natin na meron silang 15. And then, Pasay to Bulacan, meron naman silang 15 again. And then, lastly, Bulacan to QC, meron naman silang 25. So, itong mga value na to is ipag-a-add lang natin para makuha natin yung total distance na magagawa nitong traveler na to sa unang ruta na kinuha natin. So, kapag pinag-add natin lahat yung value na yan, makakakuha tayo ng 70 kilometers. So, moving forward sa pangalawang value, which is yung QC to Pasay na merong 7 kilometers, Pasay to Bulacan na merong 15 kilometers, Bulacan to Manila na merong 20 kilometers, Manila to Pasig na merong 5 kilometers, and then Pasig to QC na merong 14 kilometers. Kapag pinag-add naman natin itong mga weighted value na to, which is sa ruta nating pangalawa na color green, ito yung ang lalabas is 61 kilometers. So, sa panghuling ruta, since tatlo yung hinahanap natin, which is yung route 3, na from QC to Bulacan, meron tayong 25 kilometers. Bulacan to Manila na merong 20 kilometers. Manila to Pasay na merong 9 kilometers. Pasay to Pasig, 15 kilometers. And then Pasig pabalik ng QC, meron tayong 14 kilometers. Kapag pinag-add natin itong lahat na distance, makakakuha tayo ng 83 kilometers. So, sa tatlong ruta na yon, nakikita natin na yung route 2, yung pinaka-maikling kilometer or distance na makukuha natin sa pagta-travel natin sa QC papunta sa iba't ibang city and pabalik again sa QC. So, dito is makikita natin yung importance ng weighted graph. So, for example, ikaw gusto mo mag-travel kung saan-saan. So, through weighted graphs, malalaman natin kung ano yung pinakamabilis at pinakamurang paraan kung paano tayo makakapag-travel and makakabalik sa pinuntahan natin or sa pinanggalingan natin. Yun lamang para sa weighted graphs. Thank you.
Present day everyone, my name is Neil Cedric Sudario and I am going to report about the GC algorithm measure. So, let's read the instruction first. Choose a vertex to start at, then traverse along the connected edge that has the smallest weight. If two or more edges have the same weight, pick anyone. I will give an example of a planar and inside it ay merong mga vertex. Each vertex corresponds with each given point or value. So, mamimili muna tayo ng point na pagsisimulan natin at mga vertex papunta sa point B. For example, ito yung point A at ito yung point B. Para makapunta tayo dito, ay kakailanganin natin ng vertex with the smallest value. At kapag may nakita tayong vertex na same amount of value, ay mamimili tayo ng kahit ano, basta makapunta tayo ng A to B. Number 2. After arriving at the next vertex, travel siya along the edge of the smallest weight that connects to a vertex not yet visited. Continue this process until you have visited all the vertices. So, di ba nasa point B ka na? Pupunta ka naman sa point C. At kailangan dumaan tayo sa mga hindi pa natin nadadaanan. At isa pa rito, kailangan pa rin natin daanan ay yung pinakamababang value ng vertices. Number 3, return to the starting vertex. Kapag nakapunta tayo sa last point, babalik na tayo sa point A. And another trivia, the Cheese algorithm measure is also called greedy algorithm because it allows us to choose the cheapest option to every chance we get. So, it is the planar na in-example ko kanina. So, inside it, our vertex correspond with each given value. And those are 14, 11, 4, 5, 7, and so on and so forth. So, mag-i-start muna tayo sa letter A. Start at vertex A. The weights of the edge from A are 13, 5, 4, 15, and 8. The smallest is yung 4. So, i-connect natin yung A to D. Lagi natin tatandaan na ang pinakamaliit dapat ang pinipili natin. At kapag nasa point D na tayo, the edge with the smallest weight is letter B. So, i-connect natin yung B. Kasi 8, 7, 4, 2, and 12 are yung mga option natin. Yung 4 na daanan na natin. So, yung pinakamaliit na lang is yung number 2, which is papunta sa V. So, at point D, the edge with the smallest weight is letter F, which is 5. At pag nasa F ka na, the edge with the smallest weight is 7, which you can connect the FD. However, D has already been visited. So, napuntahan na natin yung letter D. Kaya, ang pipili naman natin ay letter F to E. At vertex E, the edge with the smallest weight whose vertex has not been visited or yung hindi mo natin napupuntahan is yung letter C. At yun yung pinakamaliit din na value. At kapag nasa letter C na tayo at napuntahan na natin lahat ng value, all the vertices have been visited, so we are at the step 3 of the algorithm. We return to the starting point or yung vertex A. Kapag natapos na natin sila i-connect at mapuntahan lahat ng points, ay ipagpa-plus na natin sila. 4 plus 2 plus 5 plus 10, 6 plus 15 is equals to 42. That's all. Thank you.
The edge picking algorithm. In this algorithm, there are 3 steps if gagamitin natin to. First, you need to mark the edge of the smallest weight in the graph. If dalawa man or more yung edges na magkaparehas yung weight, you just need to pick one. Second is, kailangan mo uli i-mark yung next smallest weight sa graph, as long as it does not complete a circuit and does not add third marked edge to a single vertex. Then, continue this process until wala ka na ma-mark na edges. Then mark the final edge that completes the Hamiltonian circuit. So here's an example na figure na pwede natin gamitin when we're going to use the edge picking algorithm. We first highlight the smallest weight, namely BD, with a weight of 2. Then next na i-mark natin is yung smallest weight uli, which is yung AD with a weight of 4. So the next smallest weight is 5. So as you can see sa figure, nag-a-appear siya twice sa edges ng AE and FB. We can mark the both of them. So the next smallest weight is 6. Meron uling dalawang edges na magkaparehas, which is yung BC and EC. So, hindi natin pwede i-mark yung BC kasi mag-a-add siya ng third mark sa vertex neto. So, we're just going to mark the edge of the EC. So, we are now at step 3 o yung pinaka-last step for the edge-picking algorithm. So, yung ima-mark natin na edge will either complete the circuit or mag-a-add ng third edge sa vertex neto. So, we need to mark the final edge para makompleto natin yung Hamiltonian circuit, which is yung FC para matapos na natin yung circuit. Natapos na natin yung step-by-step process for this algorithm. Beginning at vertex A, in conclusion, the Hamiltonian circuit is A, D, B, F, C, E, A. In the reverse direction naman, the equivalent circuit is A, E, C, F, B, D, A. Para matotal natin yung buong weight ng circuit, we just need to add those edges one by one. So 4 plus 2 plus 5 plus 14 plus 6 plus 5 is equals to 36. So yung total weight ng circuit is 36. Take note, in previous examples ng dalawang algorithms, give different Hamiltonian circuits. And sa case ng edge-picking algorithm, give the more efficient route. Why is this the best route? Or is this the best route? Actually, algorithms are very helpful, but there is no non-efficient method for finding the best vary circuit. In fact, yung ginamit nating third Hamiltonian circuit, which is ADFBCEA, in the last problem, has a total weight of 33, which is smaller siya sa mga weight na mga routes na ginamit sa mga ibang algorithms. So that's all for the edge-picking algorithm. Hope you learned something from me.
Throughout the discussion, we have learned a lot about graphs, and we also know that they are very useful in showing the connections between two objects. Now, we will be coloring them. So this is graph coloring. In the mid-1800s, Francis Guthrie was trying to color a map of England. So after several attempts, that he noticed that only 4 colors were needed to color the map. So this observation became known as the 4-color theorem. In the 4-color theorem, we can color the graph with 4 or fewer colors so that neighboring countries or neighboring vertices are not the same color. So every planar graph is 4-colorable. So here in this example, this is a map of the United States. It is colored similarly in the 4-color theorem. So there are not more than 4 colors in this map. So now we will discuss a general guide to map coloring. So first, draw a vertex in each country and then connect the 2 vertices with an edge if the corresponding countries are neighbors. And that also means that the 2 vertices are adjacent to each other. And if an edge is drawn between those 2 vertices, that means that they are neighbors. So now, to color the vertices of the resulting graph so that no edges or vertices are the same color. That means that if 2 vertices are adjacent to each other or they are connected by an edge, they cannot be the same color. And we will need at least 2 colors. So one strategy is to simply pick a starting vertex, give it a color, and then assign colors to the connected vertices one by one. But make sure that adjacent vertices are not the same color. So try to reuse the same colors and use a new color only when there is no other option. The map below shows countries labeled as letters of a continent. So assume that no country is split into more than one piece, and countries that touch each other at just a corner will not be considered neighbors. So that means that if they just touch, not really neighbors. So like this, if their borders are like this, they are neighbors. But they only touch at the point, they are not neighbors, or they are not adjacent to each other. Now each country is represented by a vertex. And then it is placed anywhere as long as it is within the boundary of that country. Then connect the 2 vertices with an edge if the 2 corresponding countries are neighbors, that is, if they share a common boundary. So erasing the boundaries of the countries, we are left with the graph in the figure below. So this is a planar graph. A planar graph is a graph that shows countries that are neighbor to each other, and it also means that no edges will cross each other. In coloring a map, we need to know how many colors we are going to use. So how many different colors will be required? So if a map can be colored by using only 4 colors, then the map is 4 colorable. But if the map can be colored using only 3 colors, the map is 3 colorable. So from the figure earlier, we will start coloring at point P. So if point B is blue, then point A is green. And point B is blue, point G is red. Why? Because it cannot be green because A is already green. So they are neighboring countries. That means that point B and point G has to be different colors. They cannot have the same colors. But point B and point D can have different colors because they are not neighboring countries. So using a graph to color a map. The fictional map below shows the boundaries of countries on a rectangular continent. So we're going to make a map using this one. A planar graph to be more exact. For this map, we will need 4 colors because the map is 4 colorable. So as mentioned before, if the map can be colored by 4 colors, it is a 4 colorable map. So each area or each country is represented by a vertex, and it is connected by an edge if they are neighbors. So as you can see, they are colored with 4 colors, and no point that is adjacent to each other or neighbor to each other are the same color. Now we color each country the same color as the corresponding vertex, and it will look like this. As you can see, no countries that are next to each other or neighbors are the same color. But if they meet at a point, they are not considered neighbors, right? So it's okay if they are the same color, as long as they are not really adjacent or beside each other. If they meet at a point, it's okay that they're the same color. This table is a scheduling application of graph coloring with 8 different school clubs who wants to schedule meetings on the last day of the semester. So some of the clubs share the same members and they want to have a meeting on the last day of the semester. So they want to schedule it wherein everyone can attend, but they have to make sure that they know which members are in the same clubs. For example, in ski club and student government, they have students who are attending both clubs. So they can't have a meeting at the same time. Using the table, we now have this graph. So in this graph, we can see which club have the same members. Like for example, the student councils have 4 clubs with the same member as them. 2 clubs that are connected by an edge cannot meet simultaneously. So if we let a color correspond to a time slot, then we need to find the color of a graph that uses the fewest possible number of colors. 2 clubs that are connected by an edge cannot meet simultaneously. So if each time slot is represented by a color, we need the fewest number of colors possible. So by trial and error, we find out that this graph can be colored by 3 colors. So that means we have 3 time slots. So if we arrange it according to the colors that we have, the first time slot is for the ski club, debate club, and student newspaper. The second time slot is for the student government, community outreach. So only 2 clubs will meet at that time. And for the third slot, it is the honor society, campus Democrats, and campus Republicans. So this is it for the graph coloring.